In fluid dynamics, the Euler equations are a set of quasi-linear hyperbolic equations governing adiabatic and inviscid flow. They are named after Leonhard Euler. The equations represent Cauchy equations of conservation of mass, and balance of momentum and energy, and can be seen as particular Navier-Stokes equations with zero viscosity and zero thermal conductivity. In fact, Euler equations can be obtained by linearization of some more precise continuity equations like Navier-Stokes equations in a local equilibrium state, given by a Maxwellian. The Euler equations can be applied to incompressible and to compressible flow, assuming the flow velocity is a solenoidal field, or using another appropriate energy equation respectively. Historically, only the incompressible equations have been derived by Euler. However, fluid dynamics literature often refers to the full set, including the energy equation, of the more general compressible equations together as the Euler equations. From the mathematical point of view, Euler equations are notably hyperbolic conservation equations in the case without external field. In fact, like any Cauchy equation, the Euler equations originally formulated in convective form can also be put in their conservation form. The conservation form emphasizes the mathematical interpretation of the equations as conservation equations through a control volume fixed in space, and is the most important for these equations also from a numerical point of view. The convective form emphasizes changes to the state in a frame of reference moving with the fluid. History. The Euler equations first appeared in published form in Euler's article, Principes généraux du mouvement des fluides, published in Mémoires de l'Académie des Sciences de Berlin in 1757. They were among the first partial differential equations to be written down. At the time Euler published his work, the system of equations consisted of the momentum and continuity equations, and thus was underdetermined except in the case of an incompressible fluid. An additional equation, which was later to be called the adiabatic condition, was supplied by Pierre-Simon Laplace in 1816. During the second half of the 19th century, it was found that the equation related to the balance of energy must at all times be kept, while the adiabatic condition is a consequence of the fundamental laws in the case of smooth solutions. With the discovery of the special theory of relativity, the concepts of energy density, momentum density, and stress were unified into the concept of the stress-energy tensor, and energy and momentum were likewise unified into a single concept, the energy-momentum vector. Incompressible Euler equations with constant and uniform density. In convective form, the incompressible Euler equations in case of density constant in time and uniform in space are, where is the flow velocity vector, with components in a n-dimensional space, denotes the material derivative in time, denotes the scalar product, is the Nabla operator, here used in the flow velocity divergence, and in flow velocity and specific pressure gradients, and is the convective operator, is the specific thermodynamic work. The internal source term represents body accelerations acting on the continuum, for example gravity, inertial accelerations, electric field acceleration, and so on. The first equation is the Euler momentum equation with uniform density. By expanding the material derivative, the equations become. In fact, for a flow with uniform density, the following identity holds. Where is the mechanic pressure? The second equation is the incompressible constraint, stating the flow velocity is a solenoidal field. Notably, the continuity equation would be required also in this incompressible case as an additional third equation in case of density varying in time or varying in space. For example, with density uniform but varying in time, the continuity equation to be added to the above set would correspond to. So the case of constant and uniform density is the only one not requiring the continuity equation as additional equation regardless of the presence or absence of the incompressible constraint. In fact, The case of incompressible Euler equations with constant and uniform density being analyzed is a toy model featuring only two simplified equations, so it is ideal for didactical purposes even if with limited physical relevancy. The equations above thus represent respectively conservation of mass and momentum in 3D, for example, and the end vectors or explicitly in flow velocity and pressure of the so-called physical variables. These equations may be expressed in subscript notation, where the n subscripts label the n-dimensional space components. These equations may be more succinctly expressed using Einstein notation, where the n subscripts label the n-dimensional space components, and is the Kronecker delta in 3D, and the n-vectors or explicitly n, and matched indices imply a sum over those indices and n properties. Although Euler first presented these equations in 1755, many fundamental questions about them remain unanswered. In 3 space dimensions it is not even known whether solutions of the equations are defined for all time or if they form singularities. Smooth solutions of the free equations satisfy the conservation of specific kinetic energy. In the one-dimensional case without the source term, the momentum equation becomes the inviscid Burger's equation. This is a model equation giving many insights on Euler equations. Non-dimensionalization: in order to make the equations dimensionless, a characteristic length and a characteristic velocity need to be defined. These should be chosen such that the dimensionless variables are all of order 1. The following dimensionless variables are thus obtained, and of the field unit vector. Substitution of these inversed relations in Euler equations, defining the Froude number, yields Euler equations in the Froude limit are named free equations and are conservative. The limit of high Froude numbers is thus notable and can be studied with perturbation theory. Conservation form: the conservation form emphasizes the mathematical properties of Euler equations, and especially the contracted form is often the most convenient one for computational fluid dynamics simulations. Computationally, there are some advantages in using the conserved variables. This gives rise to a large class of numerical methods called conservative methods. The free Euler equations are conservative, in the sense they are equivalent to a conservation equation, or simply in Einstein notation, where the conservation quantity in this case is a vector, and is a flux matrix. This can be simply proved. Demonstration of the conservation form: first, the following identities hold, where denotes the outer product. The same identities expressed in Einstein notation are, where I is the identity matrix with dimension n and delta ij its general element, the Kronecker delta. Thanks to these vector identities, the incompressible Euler equations with constant and uniform density and without external field can be put in the so-called conservation differential form, with vector notation, or with Einstein notation. Then incompressible Euler equations with uniform density have conservation variables. Note that in the second component U is by itself a vector, with length n, so Y has length n plus 1 and F has size n. In 3D, for example, Y has length 4, I has size 3 by 3 and F has size 3 by 4, so the explicit forms are. At large, Euler equations can be recast into the particular equation. Spatial dimensions for certain problems, especially when used to analyze compressible flow in a duct or in case the flow is cylindrically or spherically symmetric. The one-dimensional Euler equations are a useful first approximation. Generally, the Euler equations are solved by Riemann's method of characteristics. This involves finding curves in plane of independent variables along which partial differential equations degenerate into ordinary differential equations. Numerical solutions of the Euler equations rely heavily on the method of characteristics. Incompressible Euler equations. In convective form, the incompressible Euler equations in case of density variable in space are, where the additional variables are, is the fluid mass density, is the pressure, The first equation, which is the new one, is the incompressible continuity equation. In fact, the general continuity equation would be, but here the last term is identically zero for the incompressibility constraint. Conservation form. The incompressible Euler equations in the Froude limit are equivalent to a single conservation equation with conserved quantity and associated flux respectively. Here has length n plus 2 and has size n. In general, Euler equations are expressible as conservation variables. The variables for the equations in conservation form are not yet optimized. In fact, we could define, where is the momentum density, a conservation variable? Where is the force density, a conservation variable? Euler equations. In differential convective form, the compressible Euler equations can be written shortly with the material derivative notation, where the additional variables here is the specific internal energy. The equations above thus represent conservation of mass, momentum, and energy. The energy equation expressed in the variable internal energy allows to understand the link with the incompressible case, but it is not in the simplest form. Mass density, flow velocity and pressure are the so-called convective variables, while mass density, momentum density and total energy density are the so-called conserved variables. If one explicitates the material derivative, the equations above are incompressible constraint. Coming back to the incompressible case, it now becomes apparent that the incompressible constraint typical of the former cases actually is a particular form valid for incompressible flows of the energy equation, and not of the mass equation. In particular, the incompressible constraint corresponds to the following very simple energy equation. Thus, for an incompressible inviscid fluid, the specific internal energy is constant along the flow lines. Also, in a time-dependent flow, the pressure in an incompressible flow acts like a Lagrange multiplier, being the multiplier of the incompressible constraint in the energy equation, and consequently in incompressible flows it has no thermodynamic meaning. In fact, thermodynamics is typical of compressible flows and degenerates in incompressible flows. Basing on the mass conservation equation, one can put this equation in the conservation form, meaning that for an incompressible inviscid non-conductive flow a continuity equation holds for the internal energy. Enthalpy conservation, since by definition the specific enthalpy is the material derivative of the specific internal energy, can be expressed as then by substituting the momentum equation in this expression, one obtains, and by substituting the latter in the energy equation, one obtains that's the enthalpy expression for the Euler energy equation. In a reference frame moving with an inviscid and non-conductive flow, the variation of enthalpy directly corresponds to a variation of pressure. Thermodynamic systems. In thermodynamics, the independent variables are the specific volume and the specific entropy, while the specific energy is a function of state of these two variables. Deduction of the form valid for thermodynamic systems. Considering the first equation, variable must be changed from density to specific volume, by definition. Thus the following identities hold. Then by substituting these expressions in the mass conservation equation, and by multiplication. Note that this equation is the only belonging to general continuum equations, so only this equation have the same form, for example also in Navier-Stokes equations. On the other hand, the pressure in thermodynamics is the opposite of the partial derivative of the specific internal energy with respect to the specific volume. Since the internal energy in thermodynamics is a function of the two variables aforementioned, the pressure gradient contained into the momentum equation should be explicited as. It is convenient for brevity to switch the notation for the second-order derivatives. Finally, the energy equation can be furtherly simplified in convective form by changing variable from specific energy to the specific entropy. In fact, the first law of thermodynamics in local form can be written by substituting the material derivative of the internal energy. The energy equation becomes Now the term between parentheses is identically zero according to the conservation of mass. Then the Euler energy equation becomes simply, for a thermodynamic fluid, the compressible Euler equations are consequently best written as where is the specific volume, is the flow velocity vector, is the specific entropy. Note that, in the general case and not only in the incompressible case, the energy equation means that for an inviscid thermodynamic fluid, the specific entropy is constant along the flow lines. Also in a time-dependent flow, basing on the mass conservation equation, one can put this equation in the conservation form, meaning that for an inviscid non-conductive flow a continuity equation holds for the entropy. On the other hand, the two second-order partial derivatives of the specific internal energy in the momentum equation require the specification of the fundamental equation of state of the material considered, i.e., of the specific internal energy as function of the two variables specific volume and specific entropy. Note that the fundamental equation of state contains all the thermodynamic information about the system, exactly like the couple of a thermal equation of state together with a caloric equation of state. Conservation form the Euler equations in the Froude limiter equivalent to a single conservation equation with conserved quantity and associated flux respectively. Where is the momentum density, a conservation variable, is the total energy density. Here has length n plus 2 and has size n. In general, Euler equations are expressible as where is the force density, a conservation variable. We remark that also the Euler equation even when conservative have no Riemann invariance in general. Some further assumptions are required however. We already mentioned that for a thermodynamic fluid the equation for the total energy density is equivalent to the conservation equation. Then the conservation equations in the case of a thermodynamic fluid are more simply expressed as where is the entropy density, a thermodynamic conservation variable. Another possible form for the energy equation, being particularly useful for isobarics, is where is the total enthalpy density.